Hey guys, welcome back. So in this video we'll be talking about stoichiometry. And essentially what stoichiometry is we're able to convert from one molecule or one element to another based on a reaction. And we do that essentially using something called dimensional analysis. So this will be dimensional analysis. So dimensional analysis is something we use a lot actually in our daily lives, but we don't really call it this. So an example of this would be like, let's say we have a foot and we want to know how many inches it is. Well, we already know a foot has 12 inches, but there's a more elaborate way of doing this. It's something called dimensional analysis. If we want to convert something that's a little tricky. So let's say we want to know how many inches there are in 3 yards. So we want to convert yards to inches. So the way we do that using dimensional analysis is we have 3 yards. And we use something called the conversion factor or a ratio that we know. So we know that there are 3 feet in a yard. So we have 1 yard and we have 3 feet in the yard. But we're not done. We want to find how many inches there are. So 1 foot, 12 inches. And so we get that. When we multiply this, let me double check. Yeah, so 108 inches. So this is dimensional analysis. And you notice here already, we have this conversion factor. Sorry, that's really bad. But we have this conversion factor. 3 feet is equal to 1 yard, and 1 foot is equal to 12 inches. So we couldn't have done dimensional analysis without knowing these ratios. And we also noticed that the units cancel out. So feet, yard to yards. Numerator and denominator. So these cancel out and we left with 3 times 3 times 12 inches, which is 108 inches. Now we can relate this to chemistry. But as you saw with that dimensional analysis example, we can't really go far without knowing the ratios, the conversion factors. So let's talk about some of these conversion factors. We'll call them stoichiometric ratios. It's a big word, but it really does mean something. So these are conversion factors that we use to get something in terms of another in chemistry. So let's start with the first one. 1 mole is 6.02 times 10 to the 23 molecules or atoms. Depends. So what this says is for every 1 mole of a substance. So a mole is like, it's like a dozen, it's like a pair. It's essentially just a term of measure that we use in chemistry a lot. So 1 mole of any substance, any element, any compound has 6.02 times 10 to the 23 molecules or atoms. This is Avogadro's number, and we'll use this a lot in stoichiometry. So that's one ratio we can use. Another ratio we can use is something called molar mass. So let's say for carbon dioxide, so for every mole of carbon dioxide, 6.02 times 10 to the 23 molecules of carbon dioxide, it weighs 44 grams. So I got this number called the molar mass I got this number by multiplying each of the atoms in carbon dioxide, each of their specific masses from the periodic table. I added them all together and I was able to get 44 grams. So for instance, carbon has a molar mass of about 12 grams per mole. Oxygen has a molar mass of about 16 grams per mole. So I do this times 2, 12 plus 16 times 2 equals 44. That's how you get molar mass. 1 mole of carbon dioxide is 44 grams. This is another conversion factor that we can use. So with those two conversion factors, we can get started about how we use stoichiometry. So let's say we have a reaction here, the combustion of methane. So methane plus oxygen yields carbon dioxide and water. We can't do stoichiometry without balancing this. I can't stress this enough. A lot of times we'll have problems where they're unbalanced and we decide to do stoichiometry with it immediately without balancing it, and all our answers will be wrong 100% of the time. So we have to balance this first. So we see carbon, carbon, same number of carbons on both sides, so no coefficients we need to put. 4 hydrogens, 2 hydrogens, so I'm going to put a 2 here. And we have 2 oxygens and 4 oxygens, so I'll put a 2 here. So this is a balanced reaction. So now we can do some stoichiometry. So let's say we have, I'm just going to pull a number here. We have 32 grams of methane. And we want to see how many grams of carbon dioxide there will be. So let's use stoichiometry. So we have 32 grams of methane. And we want to convert this to moles of methane. Before we can convert methane to carbon dioxide, we have to convert this mass into moles of methane, convert the moles of methane into moles of carbon dioxide, and then convert that into the grams of carbon dioxide. So we should always sort of find the number of moles of what we have first. So we have use a conversion factor. 1 mole of methane is how many grams? So we have to first do the molar mass. So the molar mass of methane is 4 times 1 plus 12, so 16 grams. So 16 grams, a mole of methane is 16 grams. So we now have moles of methane. So now we have to convert moles of methane into moles of carbon dioxide. And we do that using the coefficients. The balanced reaction gives us the ratios of all the reactants and products. So for every 1 mole of methane, there is 1 mole of carbon dioxide. So for every 1 mole of methane, convert that into 1 mole of carbon dioxide. Now we want this in terms of grams. So we have to do molar mass again. So we have 1 mole of carbon dioxide. And we do the same thing here. So we already did this previously, but let's do it again. 16 times 2 for oxygen plus 12. So we get 44 grams. So now when we calculate this, I have a calculator right here. We have 32. So we have 32 times 44 divided by 16. We have 88 grams of carbon dioxide of CO2. So this is our answer. So now what this tells us is for every 32 grams of methane that's combusted with excess oxygen, we'll talk about this probably in a later video, but with 32 grams of methane, we get 88 grams of carbon dioxide at the end. So for the remaining part of this video, I have a little problem here. We have the reaction, the double replacement of magnesium nitrate and silver iodide. And we have 13 grams of silver iodide, and we assume that magnesium nitrate is in excess. So how many moles of silver nitrate and how many grams of magnesium nitrate do we get after this reaction goes to completion? So if you want, pause this video right now. I'll go over how to do it in probably a few seconds. Alright, so we have 13 grams of silver iodide, 13 grams AgI. Sorry for the bad handwriting, guys. So we find molar mass. I'm just going to go ahead and look that up really quickly. Silver iodide, molar mass. Where are you? Wait. Okay, so the molar mass right now is for silver iodide is 234.8 grams. So 234.8, 1 mole of silver iodide. Remember, grams, they cancel out, and that's how we put the conversion factors. So we want to convert moles of silver iodide to moles of silver nitrate. But remember, I can't do anything without balancing this reaction. Is this balanced? It's not. So let's go ahead and balance this. Magnesium, 1. Okay, magnesium's balanced. Let's look at nitrate. There are 2 nitrates on the reactant side and only 1 here. So let's add a 2 here. The iodide is also not balanced. So let's add a 2 here. And we notice that now it's balanced. But if we didn't balance it, notice we would have put a 1 and a 1 here and everything would have been different. But it turns out, when we put 2 moles of silver iodide, it's pretty much the same thing. But remember, it's always good to have this balanced, or else we would probably get the wrong answer. So now we want to convert this to moles. Want to convert this to moles of silver nitrate, and we have moles here. So we can automatically just calculate this. So let's do that. So we have 13 grams times 2 divided by 2 divided by 234.8. So we get a really small value, about 0.055 moles of silver nitrate. And that's fine, because you notice that we have such a small mass of silver iodide to begin with, but the molar mass is so big. So we expect a really small answer for this. So let's do the same thing here for magnesium nitrate. So we have 13 grams of silver iodide, same starting point. And again, we use the same sort of conversion factors. 1 mole of silver iodide is 234.8 grams. That's the molar mass. And 1 mole of silver iodide, or let's say 2 moles actually. 2 moles of silver iodide, and that 2 comes from here, the stoichiometric coefficient. And that correlates to, where do we want to go? We want to go to magnesium nitrate. So magnesium nitrate, 1 mole, based on the balanced reaction. So 1 mole of magnesium nitrate. Okay, let's get that. And we want, this time we go a step further, we want grams. So let's do molar mass again. Magnesium nitrate. And let's look at molar mass of magnesium nitrate really quick. Oh, that's not good. $148.3. Okay. So 148.3 grams. So let's multiply all this out. We get, so 13 times 148.3, and we divide this by 234.8, and divide that by 2 again, and we get about 4.11 grams of magnesium nitrate. So this is our ending answer. Let me know if you guys got that. That's gonna be it for this video. There's a lot more we do with stoichiometry. In the next video, I'll probably be talking about limiting reactants and finding a empirical / molecular formula with given data. So stay tuned for that. But a lot of the videos I'll be doing will have lots of gaps in terms of knowledge, and for those gaps in knowledge, for filling those, I think you guys should visit my website. Its link is in the description. Other than that, have a great day. Bye, guys.